of uh, of Ataberk giving the seminar here at BSC. So we are uh, happy first of all to host Ataberk last week and this week. So let me very briefly introduce Ataberk, but I don't think that it needs too much introduction because he has already given one talk a few days ago. But just in case, Ataberk is a fourth-year PhD student in the Safari Research Group at ETH Zurich, working with Professor Onur Mutlu. And his research interests include designing secure, high-performance, and energy-efficient memory systems. And his current research focus is understanding and efficiently mitigating the vulnerability caused by technology scaling in modern systems. Basically, it's about memory system, DRAM, HBM, DDR, row hammer, row press, and how FPGA could be useful for improving and understanding better this kind of phenomena in DRAM systems. So we are looking forward to your Ataberk today. So please feel free to start when you feel comfortable.
All right. Thank you, Behzat, for the cool introduction. I'm very excited to present this second part of my talk to you. So this is titled New DRAM Architectures and FPGA-Based Frameworks to Enable Fundamentally Better Computing Systems. And Behzat already introduced me, so I'm going to skip this slide. And I'll just try to motivate you about the works I'm gonna present. So computing is bottlenecked by data. I shamelessly stole these from my advisor. So these are Onur's slides. And important workloads are all data intensive. And this data requirement is continuing to increase. And for the large language models that we have today, they've been growing exponentially in size for as a few years now, and that trend is going to continue. And data-centric or memory-centric architectures can help us develop more efficient systems and combat the data movement bottlenecks. And there are many different properties a data-centric architecture could have, and I'm going to discuss a few of these today. We will start with some new DRAM architecture that enables low latency and low energy data access. So that's sector DRAM. This is a practical, energy efficient, and high performance fine-grained DRAM architecture. So I'll start by introducing you some DRAM background in case you weren't there in my first talk. So you have a processor, a memory controller inside the processor will communicate with a set of DRAM chips in a module through what we call a memory channel. That's the DDR interface, for example. And each chip contains multiple banks, and these banks share a common chip I/O interface. So I am kind of inclined to stand up because there's someone in the room, so that I feel better presenting it this way. Okay, so you have DRAM banks, and inside each bank, you have what we call DRAM subarrays. Subarrays have DRAM mats that each contain rows of DRAM cells, rows and columns of DRAM cells. And that's basically the overview of a DRAM-based system today. So this is a different view of the same picture. And it's a bit more detailed view of the DRAM subarray that I showed you earlier. We will look at this to understand DRAM row activate and DRAM read operations. So the global word line that I animate here spans the whole subarray, and it controls the local word line drivers. And the local sense amplifiers these are the local sense amplifiers. They are connected to a global sense amplifier. And this is also connected, further connected to the I/O interface. And there is some discrepancy in the data widths of these connections. So to access a row, the memory controller issues what we call an activate command. And when the chip receives this activate command, it will enable the local row buffer of the row that's being activated. And this connects these cells to their bit lines. Then the sense amplifiers, or the local row buffer, will sense the voltage deviation on the bit lines and amplify this deviation to a I/O readable value. Then we read, let's say we want to read out data from the sense amplifiers. The memory controller sends read commands for that. And then the selected column or bit lines of cells are transferred to outside the chip through the global sense amplifiers and the I/O interface. So that's inside a single subarray. Now we look at data transfer at the granularity of a DRAM module. So each chip in this module with 8 chips receives 1 byte from its data interface, and 64 bytes will make up a cache block in our example. So this chip receives these in what we call data bursts. The length of this data transfer in this example is 8 because each chip receives 8 bytes basically. Every chip receives a byte in a DRAM interface clock cycle, also referred to as a beat. And in the first beat, for example, you receive the first bytes in this cache block, in the second one, the next 8, and then so on until we transfer all the cache line. Inside the chip, this data, basically bits of the burst is eventually split across DRAM mats like such. So that's a write transfer, but you can imagine the read transfers working in the same way, but just the other way around. Now, a key problem with this, what we call coarse-grained DRAM data transfer, is that it wastes energy. Even if the processor wants to access only one word, for example, the second word in this cache block, the system retrieves the whole word of the whole cache block of this word. So you receive all 64 bytes. And the hope is that we would exploit special locality, so we would access the other bytes in the cache line. However, I mean, the processor only ends up, in this toy example, the processor only ends up accessing 8 out of the 64 words it brings. And on average, across many workloads, many prior works show that the fraction of used words are relatively low. There's also coarse-grained DRAM activation that also wastes energy. The DRAM chip activates all maps with an activate command, and it does so to transfer all words of a cache block in one data transfer burst. But activating all maps is also not required because the processor ends up not using all of those words. So we could have gone by without activating all the maps to retrieve all the words of a cache block. Then we investigate the potential energy savings a hypothetical fine-grained DRAM architecture could provide. So we evaluate 41 single-core workloads with the methodology I'll describe later. The figure on the left here shows you the energy benefits of enabling fine-grained DRAM access. That allows basically you to retrieve data from DRAM in word granularity instead of cache block granularity. And the figure on the right shows the energy improvement for, again, a hypothetical fine-grained DRAM activation architecture. And all of this just to say that, you know, the potential benefits can go relatively high. So fine-grained DRAM can provide substantial energy savings. But enabling fine-grained DRAM access and activation has 3 important challenges. And I'll describe them here and provide a classification of several prior works. But this is not a comprehensive list of prior work. These are only the relatively low cost mechanisms that we identified. So the first challenge is maintaining high DRAM data transfer throughput. We see that some fine-grained DRAM architectures reduce DRAM data transfer throughput by 8 times, which is prohibitive in terms of performance overheads. And the second challenge is, again, incurring, even though these are low cost, incurring a relatively low DRAM area overhead is still important. And we find that some of the prior work that don't reduce DRAM transfer throughput end up inducing large area overheads. And the last challenge is to exploit fine-grained DRAM, both for DRAM read and write accesses. Some of the prior works don't do fine-grained DRAM don't enable fine-grained DRAM for data transfers. We observe that basically no prior work overcomes all 3 challenges at once, and our goal is to develop a new architecture that satisfies all 3 goals at once. So for that, we designed sectored DRAM. It has 2 key components. First, we see that the modern high-performance, high-yield DRAM architectures, they already split DRAM mats, DRAM rows into mats of fixed size. They're physically isolated already. And leveraging this observation, we develop what we call sectored activation, which enables fine-grained DRAM activation at low cost. And the second observation we make is that the DRAM I/O circuitry already has a way of transmitting, you know, a selected word of a cache block in a bit of a data transfer burst. So we propose simple modifications, let's say, to that circuitry to enable fine-grained DRAM access. So I'll show you how sector activation enables fine-grained DRAM briefly. This is the example DRAM subarray from the earlier slides. If we want to enable let me see where my pointer is, these two mats, for example, and not these last two mats with DRAM row activation, we first need to isolate the global word line from the local word line drivers. So to do so, we add what we call isolation or sector transistors between the global word line and the local word line drivers. Next, we need a way of controlling the sector transistor. So we add a simple 1-bit latch, a new control signal for each mat that will determine basically which mats are enabled with an activate command. So by doing so, we transform the mat into what we call a sector, each of which can be individually activated. The second component of sector DRAM, again, is variable burst length. Let me just get rid of this. Sorry, I have a problem with this slide, but it's about to disappear. There we go. So this is an example. We have 8 sectors in a bank. Each sector sends 8 bits with a read command. These bits are collected in a buffer called read FIFO. And a relatively simple circuitry selects 8 bits from this buffer to transmit over the chip interface. The selection process is basically controlled by a burst counter that gets incremented with every beat like such. It's very simple. And then to enable variable burst length data transfers, we simply replace this burst counter with an encoder that selects the data sent out by only the enabled or valid sectors from the DRAM mats. So that's how we enable the second component. These two components, sector activation and variable burst length, can be exposed to the memory controller with no DRAM interface modifications. So no changes to the physical interface needed over the current DDR4 standard. But we have those details in the paper, so I won't go into that detail. So I'll describe very little how a modern DRAM-based computing system can effectively leverage sector DRAM. There are 2 challenges in efficiently integrating sector DRAM into systems. Today's systems transfer data between components in the memory hierarchy in cache block granularities they're designed to do that. But we need to enable sub-cache block granularity data transfers. To do that, I mean, this is only one of the things we do, but you can use sector caches whereby you extend each cache block with 1 bit of metadata for each word that indicates which word in that cache block is valid. It's very simple. And this is a substrate that enables you to transfer data in sub-cache block granularity in your processor chip, for example. And sector caches are well explored, so this is not something we invent. We just proposed using this to enable the energy savings of sector DRAM to be used in your system. Now, the second challenge is because we retrieve a word instead of the whole cache block with a single memory access, we can miss words in a cache block, and that induces additional memory accesses. Now, we developed 2 prediction techniques for this challenge. The first one basically looks at your processor's load store queue, where you accumulate load store instructions, figures out, basically coalesces the word references and subsequent load and store instructions so that you retrieve them at once. And the second one is a spatial pattern predictor that we tailor for predicting useful words in a cache block. And I won't go into the details of these, but if you have questions, I would be happy to take them later on. So I'll show you the evaluation of sector DRAM. We use a variety of simulation framework to evaluate the performance and energy efficiency of sector DRAM. This is the baseline system configuration that we use for your reference. I mean, I'm not expecting you to read all of this. And we compare sector DRAM to 3 state-of-the-art fine-grained DRAM mechanisms. Those are namely half DRAM, fine-grained activation, and partial row activation. and we simulate 41 1 to 16 core multi-programmed workloads from these benchmark suits. First, we look at the power implications, DRAM power implications of sector DRAM. We investigate the activate and read power. So write power closely resembles that of read, so I don't show it as a separate plot here. The x-axis shows you the number of sectors we activate or read with each command, and this is the power consumption broken down to array power and periphery power inside the DRAM chip for activating or reading 8 sectors, and this is the rest of the plot. We make 2 observations from this. So the first one is that reading or activating 1 sector, and this is what we expected, can greatly reduce power consumption compared to reading or activating all 8 sectors. And the second is that the activate power is dominated by periphery power, which does not, or which is marginally affected by the number of sectors we activate. So the most power reduction we get for read commands rather than activate commands. So this is a speed up. This is a little bit complicated plot, but I'll walk you through it. This will show the distribution of speed up across all tested workloads, categorized according to the number of last level cache misses. So that's high MPKI, medium, and low MPKI. That is to say, basically, high MPKI has very high memory intensity. So most of the memory accesses end up going to DRAM. And the boxes on the left, so there will be 2 boxes on every x-axis, on top of every x-axis value. The one on the left is for the baseline system. The one on the right is sector DRAM. The x-axis shows you the number of cores. So the multi-programmed, so basically this is a single core workload, the others are multi-programmed workloads. And the y-axis is the parallel speed up, normalized to the baseline system, executing the same workload on a single core. So that is to say, basically, the higher a point in this plot, the better the performance for that workload. And these are the speed ups for dual core workloads, and this is the rest. So we observe that sector DRAM provides significant speed ups for highly memory intensive workloads when core count is higher than 2. Basically, I would summarize that as workloads that create high contention for the memory system, in the memory system. And second, sector DRAM provides smaller parallel speedup than baseline for non-memory intensive workloads because the benefits of sector DRAM diminish with additional memory access is caused by sector misses. Sector misses when you retrieve one word in a cache block, you don't retrieve the other words, and you miss some of the other words, so you need to do another memory access. We have a way of alleviating that performance degradation. The key idea is to basically fetch all sectors of a cache block, go back to the baseline system configuration per se, or disable sector DRAM if the workload access patterns are not going to benefit from sector DRAM. At a very high level, we propose measuring the average number of requests in the memory controller's request queue that indicates, the memory intensity of the workload. If the occupancy or if the number of requests is higher than a certain threshold, then we enable sector DRAM. And here we show weighted speed up for heterogeneous workload mixes for 3 memory intensity categories. And I just want to say basically that the dynamic policy that selectively enables sector DRAM reduces the performance overheads and basically matches the performance almost of the baseline system. So that's performance. We look at energy benefits also. Similar to the speed up results, sector DRAM provides significant energy savings for memory intensive workloads. And we compare sector DRAM to prior work. It outperforms all but half DRAM. And that's because half DRAM is not subject to the overheads of sector misses. I'm going rather fast over these comparison slides. In terms of energy consumption, sector DRAM outperforms all prior fine-grained DRAM architectures. And the main reason for that is, first, we try to make DRAM data transfers as high throughput as possible. The second reason is we enable fine-grained DRAM activation at the granularity of a word, whereas, for example, half DRAM can only enable half of a row, and therefore, and it doesn't enable fine-grained data transfers, just fine-grained activation. We estimate sector DRAM and processor area overheads. We find that sector DRAM components take up 1.7% of a DDR4 chip's area. This is again an estimation to the tools that are with the tools that are available to us, and the sector caches and the sector predictor in the processor take up 1.2%, an estimated 1.2% of a relatively large 8-core processor's area. There are more details in the paper that I won't be able to discuss. We have a micro benchmark performance evaluation. I think this is important. Sector DRAM greatly improves performance for random access workloads because they have the characteristics that benefit most from sector DRAM. So for example, if your workload is randomly accessing words in the main memory, then those accesses are gonna happen fast with lower energy than the baseline system. We have sensitivity studies and discussion on how we can enable finer grained sectors, that is more than 8 sectors in a row, and the compatibility with DRAM ECC. It is compatible with ECC. And I invite you to read the paper for details. So in the interest of time, I won't summarize sector DRAM. We have the extended version on archive. The infrastructure is open source. I will highlight these. And I'll move on to the next project. But I'll just stop a few seconds to take questions, if there's any. Okay. So I'm assuming I cannot see the chat right now, so you can speak up if you have questions. I'm completely fine with that. But I'll continue, and you can interrupt me. So I'll be moving on to describing some FPGA-based prototypes or frameworks that enables processing in memory research, I think. So this is PyDRAM, an FPGA-based framework for end-to-end evaluation of processing in DRAM techniques. I will walk you through this slide very quickly. This is just some additional background, just to show what sequence of commands we typically have when we want to access DRAM, and we covered this to some extent. But if you want to access a cell on this in the first row in this figure, lost my pointer there. Okay, there we go. You need to send an activate command to that row. In doing so, you will fetch the data to the sense amplifiers. So now you can access data there with read commands. Then you will need to send a precharge command eventually if you want to access another row. Precharge command will disable the word line driver and precharge the bit line, so the bank is ready for another access. And then you can activate another row and access that row. So there are some things called the timing parameters in the DRAM standard that we must obey to ensure reliable operation. One important parameter is called the activation latency. That defines the delay between an activate command and the next precharge command. There's the precharge latency between precharge and activate command, and there's this access latency. That's the delay between an activate command and the preceding read command. So we must obey these if we want reliable operations, but I'll show you interesting things happen reliably if you don't obey them. So I will briefly introduce processing and memory techniques. I'm going to stick to ones that are that can be done in real chips today. So these are commodity DRAM-based processing and memory techniques. They use operational principles of DRAM to move data within memory or do interesting operation analog majority operations, for example. There are two examples that are relevant to us: row copy and true random number generation for this work specifically. Row copy is basically you can copy data at row granularity. So you can take one row and copy it, move it to another row inside DRAM. You don't take data outside the subarray for this. And true random number generation, I will describe later in detail. There are many other things you can do, and now there's even more. This slide is slightly outdated, but let me give you the key idea of row clone, that is bulk data copy. We want to copy this orange source row to the destination row. So we can do that in 2 steps. We first copy the source row to the sense amplifiers, and then we must copy this row back to the destination row and overwrite the data there. Now we can do the first operation by just sending an activate command. This is already supported in the standard. And we can actually do the second one, that is without without pre-charging the bank, we can overwrite the data in the destination row with the sense amplifiers, with what's in the sense amplifiers. We use what we call carefully crafted sequence of DRAM commands, but it's really an activate, pre-charge, activate command sequence. The key is if you obey the timing parameters, this command sequence will just activate the row S here, just an arbitrary row. And then when you send the pre-charge command, the bank will be pre-charged. The next activate command will activate row D regularly. No copy going on. But if you violate the DRAM timing parameters, that's to say you bring these commands closer in time, you can activate row S and the pre-charge command is somehow ignored by the DRAM chip. So then you activate row D. That enables you to overwrite data in row D with the data in the source row. If you have any questions, I'll take them, but I won't go into the details of how this works. So I'll move on to the other interesting processing in memory technique, which is random number generation. This was described in the D-range paper. So this is DRAM-based random number generation. The idea is, I'm just showing you a subarray of cells, and the colors and the sizes of the cells here indicate their failure probability when we access them with a reduced access latency. So we will activate a row, and we will reduce the access latency timing parameter and violate the DRAM standard. And if we, for example, have a high failure probability, meaning when we do this operation I described, we end up with a bit flip every time, that is a high percent chance to fail row cell. There are also cells that have a very small probability of failure when we access them with reduced latency. But interestingly, there are some cells that have an exactly or very close to 50% chance of failure. So every time you repeat this operation, there's they will randomly fail or not fail. So the idea is to identify these cells and use them for random number generation. Now, these are cool techniques. They can have performance improvements. They can enable new applications, but developing system support for them requires you to make some tweaks, changes in every level of the system stack. So if you want to enable bulk data, well, if you want to accelerate some bulk data initialization application, for example, with row clone, backed up by row clone, you need to bridge this gap, and you need to implement some sort of support for custom timing parameters in the memory controller. You might need some control logic for orchestrating processing and memory operations, some software interface, maybe some additional instructions on top of your native ISA to execute PIM operations, and some sort of system support, some basic system support, like how we allocate data so that we can copy it correctly. And PyDRAM its goal is to bridge this gap, what I call the system gap, with customizable hardware software components. And the idea is this would allow users to rapidly implement new processing and memory techniques and be able to solve or work on system integration challenges of processing and memory techniques. Finally, you would also be able to use this sort of platform to analyze end-to-end implementations, show some performance results, for example. And PyDRAM has 4 key components that enable this goal. We have, on the hardware side, we have what we call a PIM operations controller, a specialized sort of memory controller for enabling support for custom timing parameters. On the software side, we have a library that the applications can use to execute PIM operations, and then some supervisor software with basic system support like memory allocation, and very simple version of virtual memory. And we attach these key components to a real computing system. So this is describing the system design we have. These are the new components we add. We in the PyDRAM prototype system, we have a RISC-V CPU core in the Rocket chip system. And we also have a DRAM module where we perform these real processing and memory operations. And the real prototype looks like this. It's in a host, it's an FPGA board in a host machine. The RISC-V system has a simple in-order RISC-V core, a very wimpy core per se, and there is a PIM, what we call a PIM-enabled DIMM from Micron, where we perform real processing and memory operations. We study the integration challenges of row clone with this infrastructure. There are a few challenges. The first one is memory allocation. I will go into the details of that. And the second one is memory coherency. So coherency, I will describe quickly here. Basically, because we're computing in data in DRAM, we should invalidate or flush any cached copies, basically, in the process before we do some sort of computation on it. So to deal with that, we implement very simple CL flush instructions in the RISC-V CPU core. And we use these to evict the cache block from the CPU caches to the DRAM module before we perform a row clone operation, for example. And the first challenge is about memory allocation. So here I'm showing you 4 different memory allocation options for a source and target, or source to destination operands, copy operands. If you have this mapping 1, this operation would yield incorrect results because you don't know what data is here in the row that target 1 belongs to. So I forgot to describe, these are different banks in your DRAM chip, and these are different subarrays. So every rectangle here is a DRAM row, and this is showing you how you put data in different scenarios. The first scenario doesn't work because you would overwrite data that's here with data that you don't know that's here. The second one does not make sense because you can copy data across cells on the same bit line. So there's no way you can move source 2 to target 2 because they have different offsets in their rows. The third mapping is also not possible because row clone operations are only supported for now within a subarray. You cannot copy data across subarrays. And the fourth is an example that works. And we have implemented a new memory allocation function in the supervisor software, in the custom supervisor software that satisfies this 4th requirement that I showed you in the earlier slide. But this slide is showing you some details that I won't go through, and I will refer you to the paper for details on that allocation mechanism. I'll move on and describe how we evaluated row clone in PyDRAM. This is a system configuration for our prototype. And one important thing to note here is that our DRAM rows are 8 kilobytes large, so that determines our DRAM copy initialization granularity. We have to copy data in increments of 8 kilobytes. We have 2 micro benchmarks. One of them is called CPU copy that uses load store instructions to copy one array to another array. And row clone copy uses in-DRAM copy operations. And we evaluate that with and without CL flush to show the overheads of actually maintaining coherency. And then we have some other micro benchmarks that mimic the behavior of fork bench, which is just it's a benchmark for the fork system call, which creates new copies of your process, and a compile initialization heavy compile workload. And we also were able to launch spec 2006 libquantum, where we replaced calloc calls that is used to allocate data with in-DRAM initialization. So I'll show you the results of these. So this one is the throughput we have for row clone copy and row clone based initialization over CPU copy and initialization for different array sizes. We see relatively large improvements provided by Rocon. And this is relatively large because the processor, if you think about it, the processor core we have is very, very wimpy. It is a 50 megahertz clocked core, so anything this core tries to do is going to be relatively slow anyways. So this that's why we have a very high improvement for Rocon operations here. But we will get back to this, and I'll show you some more accurate representative results with a different framework that we developed on top of PyDRAM. We also investigate the overheads of CL Flash. The key outcome is that if you have to do CL Flash, meaning you have cached copies of data, the performance improvement drops down from like an average of 119x to an average of, 12 to 14x, down to 1.9, 2.3x, depending on how many of those cache lines you have in the caches are dirty. So if you have dirty cache lines, you have more overhead because you have to overwrite the data in DRAM. If you don't have dirty cache lines, you can just invalidate them. But these are the overheads. So we also have some other results. I won't go through them in detail. We have some relatively, we have meaningful speedups for the other workloads I mentioned earlier. I'll leave it at that, but if you have any questions, I'll be happy to come back to this slide. I'll show you the performance for DRAM. We also implemented DRange. So you remember the idea of DRange is to find these cells that fail with 50% probability when we access them with reduced latency. So we basically find those, identify the DRAM cache lines that have these cells, and we implement a new logic in the memory controller that periodically accesses these cells with reduced latency to buffer 1 kilobytes of like random numbers and in the memory controller. And then we provide this to the user through a rand DRAM function call. And one highlight here is like on top of the code base we have, PyDRAM's Verilog C++ code base, implementing this took like relatively small lines of code. It's not the best measure for complexity of this task, but I couldn't figure out a better measure. So this is relatively low, right? If you think about it, you can implement a new PIM operation with small changes over PyDRAM's code base to try out something new. And we evaluate this random number generated performance. This plot shows you the throughput you get with the configured TRNG period. That's the hardware logic that periodically generates random numbers. Its period can be configured from 220 nanoseconds all the way down to up to whatever you want. And we see that you can generate two random numbers at 8.3 megabits per second throughput using PyDRAM. And that's it for PyDRAM. I will kind of seg into the better version, I would say, of PyDRAM. Again, this is also open source. An extended version of the journal publication is also available on arXiv. And I have a longer talk on YouTube where I also give a tutorial on how to use PyDRAM. So you can find the link if you're interested in this. I recommend you see the video. I'll talk about EasyDRAM. So I've described some processing and memory techniques, but there are more DRAM techniques than just those. So if you violate timing parameters, you can do, yes, many interesting processing and memory operations, but also you can implement things like retention-aware intelligent array. Based on charge leakage properties of each cell, you can treat different cells differently and improve energy, for example. But you remember we need some system support to evaluate these techniques. And FPGA-based evaluation platforms like PyDRAM is a good basis for evaluating these techniques because they provide an interface with real DRAM chips so you can perform processing and memory operations in real chips. They have a relatively short end-to-end execution time compared to simulators. And the problem is they require hardware design expertise. And they have a disproportionately low CPU clock frequency that is not representative of a real system. And basically, we have a more comprehensive analysis of strengths and weaknesses of prior work and FPGA-based platforms, but that's in the paper, so I'm not describing all of the landscape here. I'll describe the first weakness in a bit more detail. So to implement a new technique, you need to modify your memory controller, and this requires deep hardware design expertise to reason about many important hardware design aspects, as you are probably very well aware. And this poses a barrier to entry for researchers that are not, hardware design experts. And the second weakness is that we observe that in a typical computing system with DRAM-based main memory, the CPU clock frequency is around 6 gigahertz, and DRAM is between 1-4, depending on what sort of DRAM module you have. And if you implement this CPU in an FPGA, it's very likely that you won't be able to achieve such high clock frequencies for that design. But the DRAM is attached to this FPGA is still operating at relatively high clock frequencies. So this discrepancy limits evaluation accuracy and skews performance results, as I've shown you in PyDRAM's results, where we saw like 1.150x speedups for Olgun. To summarize, the problem is FPGA-based platforms are good candidates for evaluating DRAM techniques, but they're difficult to modify and they yield inaccurate system performance results. And our goal is to enable rapid and accurate end-to-end evaluation for DRAM techniques without requiring deep hardware design expertise. And to that end, we develop EasyDRAM. There are two key ideas that enable, evaluating new DRAM techniques without requiring hardware expertise. The first one is a programmable memory controller. So there's a C++ program. We chose C++. I've been asked why C++, because, if you have that question, ask me, I'll answer later. This runs on a RISC-V core. And to enable accurate system performance results, we implement what we call a time scaling technique that is very difficult to describe in a short time, but essentially splits the design into different emulation domains and throttles each domain to make sure that the progress they make resemble a modern system, respectively. But I won't go into the details of the second technique. So this is an overview of EasyDRAM. The programmable memory controller I'll quickly describe because I like the programmable memory controller part. It's really a general purpose processor that runs a memory controller model instead of a conventional RTL memory controller. It's a very simple toy example of a controller program. So you have, you're waiting for a request to arrive. This is just completely abstract, right? But just to give you the idea. Then you process this request and find the row bank column address it accesses in DRAM, and then you issue this command to DRAM and then return a response. And all of this is to show that the programmable memory controller provides an easy means to perform low-level memory controller operations, and you don't have to write Verilog. And especially if you think about having to implement new scheduling algorithms, new mapping functions, new new techniques, new command sequences, and so on, it is very beneficial to have something you can program instead of having to write hardware designs. You can find more elaborate examples in the paper. I won't go into details. The challenge this introduces is that the core, the programmable memory controller core, executes many instructions to simulate one memory controller clock cycle, if you think about it. All that code I showed you, it could take hundreds of cycles to execute in that controller, in that processor core. And it creates two issues. First, you cannot issue DRAM commands at nanosecond granularity because this memory controller is too slow. And we need this functionality because we want to violate DRAM timing parameters to implement new DRAM techniques and so on. And second, the memory controller takes so long to execute commands, and this causes additional delays, very lengthy stalls in the processor of the system, of the simulated system. And this limits evaluation accuracy and skews results. It makes the situation a bit worse for this picture I described earlier. I will not describe our solution for this problem, but we have a solution for that problem, and I refer you to the paper for details. This EasyDRAM system is prototyped on a different FPGA board, VCU108. In our evaluations, we have now an out-of-order core with a relatively larger cache. It represents it is a bit more of a powerful processor than what we had for PyDRAM. And we have, again, a DDR4 DRAM chip where we perform real processing and memory operations. So we evaluate row clone. We provide a realistic performance evaluation of row clone and a technique that enables DRAM access latency reduction. I'll just describe row clone very quickly. So we have two takeaways from this study, and they relate to the PyDRAM results. We see that DRAM technique evaluation platforms that do not faithfully model a modern processor can report high benefits in favor of DRAM techniques, and row clone still significantly improves performance when compared to a modern CPU baseline. So I'm just going to flash you the results. This is EasyDRAM without time scaling. So that represents PyDRAM essentially. It reports a very high speed up for row clone over CPU copy. And again, this is in line with the results of prior work. EasyDRAM with time scaling demonstrate a smaller speed up. Like that is now 15x from 300x. So this represents reality more than what PyDRAM shows. And this is still relatively high if you think about it. And that's where I will leave you at for the evaluation of row clone. We also study DRAM access latency reduction, the DRAM access latency reduction technique. Again, I will have to refer you to the paper for that. That's it for EasyDRAM. I think I will stop again for momentarily to take questions, and I'll go through two more things, but relatively quickly. So if you have any questions about what I've presented so far, I'd be happy to take them now.
Yes, thank you, Ataberk. Yes, I think that we have 10 minutes. I think it is good to give a few minutes also for questions and discussion. So manage your time as you prefer, okay?
Yeah, so I'll go through the rest quickly, and then we will stop for questions. So that's EasyDRAM, and that concludes this processing data where it resides aspect of the talk. So now we'll just touch on intelligent data management. I think it will make sense when I describe you Metasys. This is another FPGA-based evaluation framework that we developed. And this is about cross-layer techniques. So if you look at what's done in processors today, we design hardware structures like caches, prefetchers, memory controllers, and we specialize them in predicting programmer behavior. Now, they try very hard to infer program behavior, but the idea is that programmer already kind of knows how this should behave. So cross-layer techniques envision a future where software provides useful information, that we call metadata, that the hardware is trying to infer to the hardware. For example, the software can provide data structures used and access patterns exhibited by your workload, and different parts of the application may work on different data types. And this can be communicated to hardware. And the idea is that cross-layer interaction between hardware and software can more accurately provide program metadata to hardware. And ideally, you would use this information to perform better. And Metasys' goal is so these techniques already exist, and Metasys wants to enable rapid implementation and evaluation of cross-layer techniques in real hardware. And we develop Metasys. That's an open source full system cross-layer evaluation infrastructure. I'll show you what it looks like later. And it's composed of three things. I'll describe what these are without going into too much detail. So the first one is tagged memory-based metadata management. All of this just means that you have optimization clients and metadata. Optimization clients are basically your hardware components, can be caches, can be your memory controller, and so on. We tag memory addresses with metadata IDs. So what that means is if you want to query, if you want to answer this question, is this memory address accessed frequently? You can look up the metadata ID, and then you can look up your metadata store. So it's like two levels of indirection to figure that to answer that question. Again, this is expected to be provided by the programmer, or anything that's above the, ISA layer, really. It could be the compiler, it could be something else. Then there's the cross-layer interface that enables you to define new metadata properties and map them to addresses. So these are instructions that we provide to the user of the infrastructure. And I won't go into the details of them, but finally, we provide ready-made integrations of caches, prefetchers, memory controller, and specialized bounce checking logic as optimization clients within the framework that we open source. And we evaluate a cross-layer prefetching technique for graph applications using Metasys. The key difference between this and a regular what you would see maybe in a processor code is that this uses graph data structure semantics instead of relying on program context or memory access history. So the user kind of provides this information along with the workload. And we evaluate several workloads from the Ligra benchmark suite, graph application suite. And we show that Metasys-based prefetching exceeds simple strike prefetching performance for these workloads. And it comes very close to a specialized prefetcher that's tailored for graph applications. We also study a memory safety use case, and we implement bounce check in Metasys to prevent buffer overflows, basically, unintended writes to a memory location. If you think about it, that's one way of thinking about it. And Metasys' bounce checker performs better than software bounce checking is one result we highlight. These are all just to show that Metasys allows you to evaluate various types of cross-layer techniques. And it's another one that we return address protection is another use case evaluated, but I won't show you the details. But I'll refer you to the paper if you're interested. We also characterize the overheads of implementing something like enabling cross-layer optimization techniques in hardware through what we propose in Metasys. So there are many sources of system overhead. You have to deal with all these interactions. And in the paper, we characterize the performance overheads. And I believe we have insightful results. But again, I will have to refer you to the paper if you're interested again. Please check. And this is also open source. So everything I've shown you is open source. I'll conclude very quickly with DRAM, and there's going to be some overlap between this talk and the previous talk if you attended the other talk. But this is equally important because it is why kind of what I am doing here as part of my visit. So DRAM vendor is a DRAM testing infrastructure, and we need it because there are many factors that affect DRAM reliability and performance, and they cannot be studied easily and properly using anything other than basically experimenting using real DRAM chips. And there are existing open source testing infrastructures that are available today. You could start using them, but they have various drawbacks that DRAM vendor aims to solve. And the most important thing, I think, is that it is easy to use and easy to install. Like you could download the open source repository, and if you have the FPGA, you can get it running. We support 6, now 7 out-of-the-box FPGA-based prototypes, but this slide is slightly outdated. In the paper we wrote about DRAM vendor, we evaluated its flexibility by showing multiple case studies. There are more details in the paper. This infrastructure enabled a lot of research into DRAM reliability and DRAM functionality. It allowed people to uncover new operations in DRAM chips. That like some processing and memory techniques were actually supported by real chips. And this is just like a list of research works that DRAM vendor enabled. A highlight would be row press, but I'm not going to go into details of that. But I'm going to talk a bit about how it relates to my visit. So we are trying to develop support for DRAM vendor in the MEEP cluster at Barcelona Supercomputing Center. And the potential is it will enable large-scale and flexible DRAM testing using high bandwidth memory. In the BSC MEEP cluster, you have 96 of these U55C boards. And I can with 99% confidence say that this board now supports DRAM vendor. And I'd like to thank my collaborators and Besat specifically, who's hosting my visit and collaborating with us to make this happen. So this is as part of the Severo Ochoa mobility grant program. That's kind of how I ended up visiting BSC. And I have some very preliminary results from a test system. So this is showing you, again, this is something I've not described, but DRAM is subject to redisturbance errors. If you repeatedly activate a row of DRAM, then you can induce bit flips in neighboring rows within standard operation. And this is what you see in one of the HBM2 chips in BSC. On the x-axis, you have the number of redisturbed bit flips in a row. And this shows you the distribution, like the histogram of those bit flips. So this says you have two clusters. So a majority of rows, like half of the rows, let's say, exhibit fewer than 300-ish bit flips, and the rest exhibit something above 309. So there are two means, two normal distributions per se. This is interesting, and it looks new. I've not seen this before in the HBM2 chips we tested. So this could mean a few things, assuming there are no errors in our experiments. Again, this is preliminary data, but I was excited to see this new result. And I'll make a final remark about Severo Ochoa, who's a physician and biochemist. He won the Nobel Prize for basically synthesizing RNA outside the cell for the first time. And if you're interested, he delivered a very humble Nobel Prize acceptance speech. And you can find that the link below. And the mobility grant that I'm honored to receive, it enables researchers to participate in cross-institutional research. And I think it's a great program, and I'd just like to mention it. So in summary, DRAM Bender is a good testing platform. I'll leave it at that, and it's open source. You can download and use it. And we would love to support you if you're interested in running DRAM Bender. Again, all of the things I've described are open source. I'll conclude. I've talked about a few properties of data-centric architectures and how my work relates to them. And I hope you're inspired to maybe work on this problem. I think there are adoption challenges of processing memory, and some of the work I presented can be used as tools to tackle these challenges. And I'll leave you with this list. These are what we think are potential barriers to adoption for PIM. And we believe that these can be overcome with a change of mindset from processor-centric computing view to memory-centric computing view, and with the use of our tools, hopefully. So that's it. Thank you very much for your attention. I'll be happy to take any questions.
Okay, fantastic. Thanks a lot for a very interesting talk, a lot of interesting works, research. It was very nice to see them, and that is actually a very good point that they're all open source. That's a very important point. I think that we can take a few questions, although we are almost, the time is over, but I think that it would be good to have some questions from room or from Zoom. If anybody has a question, just please speak up. Maybe quick, yes.
Thank you. I had a room audience member, but they left. So
Okay. So just one quick question from my side. So you know that we are in the age of, let's say, some state-of-the-art applications, language models. It is basically changing everything. So how do you see that? Well, you have done a lot of research around memory, right? So what I was wondering, how do you see that these new applications, what is the main drawback of the existing memory systems to basically run these applications much more efficient? Because apparently we are facing with performance limitations to run this application, right? So what is fundamentally wrong with our existing memory infrastructure, the memory controller, the microarchitecture of the DRAM? And what is the problem there? And which one of these works that you have presented you think that can be more beneficial to address those kind of issues?
Yeah, that's a good question. I mean, I'll start by saying that I am not an expert on LLMs, right? I think that's the question about LLMs, probably. Again, I'm not the best person to ask this, but I think most of what I talked about relates to LLMs in the sense that if you want to enable more efficient computers, you need to reduce data movement, and these workloads are bottlenecked by data movement. I mean, the main bottleneck they have is the memory bandwidth and capacity. The more capacity you throw at these workloads, you can enable larger scale LLMs. And the more throughput you have, which processing and memory kind of provides you with, you can enable better performance. So I guess I would leave it at that. And as for like frameworks that would enable you to develop more ideas, I think EasyDRAM is one such framework. If you have ideas, processing and memory related ideas, you can use the EasyDRAM memory controller to simulate your new idea. And you can test on real DRAM chips. Another important framework, I think, in this context is DRAM Bender, which allows you to study deeply the reliability problems, robustness issues of DRAM chips, which will get worse as we try to, scale the technology down so that we can provide the whatever these workloads need, which is more memory, more bandwidth. So I would, that's how I would, connect my work to there.
Yeah, exactly. I think that the fact that is so using the existing DRAM commodity DRAMs is very important. Also, I think that your first work you talked about sector DRAM, which I think it is basically it is a new infrastructure for DRAM. So that kind of work also could be interesting for simulation level also.
Yeah, for sure.
So I think that if there is no other questions from audience, probably we can close the talk. So thanks a lot, Ataberk. And just a comment that Ataberk will stay with us today and tomorrow here at BSC. Just feel free to reach him if you're interested to chat with him, to talk about the works, collaborations, and everything. Also, he will keep us in contact with us for collaboration. So just keep in touch, and I think that there are a lot of opportunities for collaboration together. Perfect. Thanks a
Thank
lot
you.
again, and for yourself and for education and training, and for the attendees. And have a great rest of the day.
Thank you very much. Goodbye.
Bye.